What if the next great earthquake is already loading beneath a coastline that feels perfectly safe today? What if the ocean beyond the horizon appears calm only because the forces building beneath it are invisible? And what if some of Earth's most dangerous faults are not the ones shaking every week, but the ones that have remained silent for generations? Far beneath the world's oceans, immense slabs of Earth's crust are engaged in a slow collision that never stops. Every second, every minute, every year, entire tectonic plates grind against one another. The movement is almost impossible for humans to notice. It happens at speeds comparable to the growth of a fingernail. Yet over decades and centuries, those tiny motions accumulate into one of the most powerful natural processes on the planet. Scientists call these boundaries subduction zones. At these locations, one tectonic plate sinks beneath another and descends into the mantle. The contact surface between them can stretch for hundreds or even thousands of kilometers. When the plates become locked together, they continue trying to move despite being stuck. Stress accumulates, rock deforms, energy builds. Eventually, something gives way. When it does, the result can be a megathrust earthquake, the largest type of earthquake Earth can produce. These are not ordinary earthquakes. They are capable of rupturing fault surfaces larger than entire countries. They can lift or drop the seafloor by several meters in seconds. They can launch tsunamis across entire ocean basins. They can permanently alter coastlines and reshape landscapes. The frightening reality is that many of the world's most hazardous megathrusts are not announcing their intentions through constant shaking. Quite the opposite. Some have become eerily quiet. Modern satellite geodesy, seabed pressure sensors, marine seismic imaging, and paleoseismic investigations are revealing a disturbing pattern. Several major subduction zones appear to be accumulating strain faster than previously believed. Some are strongly locked despite rapid plate convergence. Others have not experienced a full margin rupture in centuries. This is not a prediction. Earthquakes do not follow schedules. No scientist can identify the date of the next great rupture. But geology can reveal where stress is accumulating and where the physical conditions exist for a future catastrophe. From the cold waters of Alaska to the tropical seas surrounding Southeast Asia, these are the 10 megathrust systems that deserve the world's attention. We begin with number 10. Number 10. Alaska Aleutian Subduction Zone. At first glance, Alaska might seem like an odd choice for the beginning of this countdown. After all, Alaska experiences earthquakes constantly. Unlike many other regions on this list, the ground here rarely stays still for long. Yet beneath the apparent activity lies one of Earth's most formidable subduction systems. The Pacific Plate moves relentlessly toward North America at roughly 50 to 70 millimeters per year, equivalent to approximately 2 to 3 inches, or about 5 to 7.6 centimeters annually. Along the Aleutian Trench, that oceanic plate bends downward and plunges beneath southern Alaska. The boundary stretches for thousands of kilometers. It is one of the longest and most complex megathrust systems on Earth. The reason Alaska ranks lower than some others is not because the hazard is small. The reason is that portions of this margin have already released significant strain during historic earthquakes. Most famous among them was the Great Alaska Earthquake of 1964. With a magnitude of approximately 9.2, it remains the second largest instrumentally recorded earthquake in human history. During that event, a fault surface hundreds of kilometers long ruptured. Entire coastal regions dropped by several meters, equivalent to several meters or several feet. Forests were drowned as seawater permanently invaded formerly dry land. Yet what interests geologists today is what happened afterward. The fault did not remain relaxed. GPS measurements show that many of the same segments have gradually become locked again. The process resembles a giant spring being compressed. As plate convergence continues, stress once again accumulates. Particularly concerning are strongly coupled regions beneath Prince William Sound, Kodiak Island, and portions of the Kenai Peninsula. In these areas, geodetic measurements indicate that the two plates remain firmly attached. The Pacific plate continues attempting to descend. North America continues resisting. The result is ongoing strain accumulation. One fascinating exception exists southwest of the main rupture zones. The Shumagon Gap appears to behave differently. Evidence suggests that this segment may release strain through aseismic creep, a process where the fault slowly slips without producing large earthquakes. Some geological records indicate that this behavior may have persisted for thousands of years. That discovery is important because it demonstrates that not all portions of a megathrust behave identically. Some lock, some creep, some alternate between the two states. Understanding these differences remains one of the biggest challenges in earthquake science. Despite these complexities, large sections of the Alaska Aleutian margin remain capable of producing magnitude 8 and larger earthquakes. The tectonic machinery continues operating exactly as it has for millions of years, and every year that passes adds more strain to the locked portions of the system. Number 9. Central Chile. The western edge of South America is one of Earth's most spectacular tectonic laboratories. Here the dense oceanic Nazca Plate dives beneath the South American continent at approximately 70 millimeters per year, equivalent to about 2.76 inches or 7 centimeters annually. The process has created the towering Andes Mountains. It has generated massive volcanic systems, and it has produced some of the largest earthquakes ever documented. Yet the danger in central Chile is not simply the speed of convergence. It is the complexity of the megathrust itself. For decades, scientists assumed that large earthquakes generally repeated similar rupture patterns through time. Then detailed studies of Chile's geological record began telling a different story. Ancient tsunami deposits, coastal uplift markers, and sediment records revealed that past great earthquakes did not always rupture identical sections of the plate boundary. Some events concentrated slip near the trench. Others penetrated deeper beneath the continent. Some ruptures were wider. Others were narrower. The implication was profound. The locked portion of the megathrust is not fixed. It evolves. This means that historical earthquake records may provide only part of the story. A region that appears quiet today may simply be storing strain differently than it did centuries ago. The 1960 Valdivia earthquake remains the benchmark for megathrust disasters. With a magnitude of approximately 9.5, it remains the largest earthquake ever measured. But even that extraordinary event may not represent the maximum possible behavior of every segment along the Chilean margin. Geodetic measurements continue showing significant coupling in several areas. The Nazca Plate is still pushing, the South American Plate is still resisting, and the deformation is ongoing. The lesson from Chile is both simple and unsettling. Silence does not mean inactivity. A fault can spend centuries preparing for a rupture whose dimensions exceed anything recorded in modern history. Number 8. Java segment of the Sunda Arc. The 21st century began with a reminder of just how devastating megathrust earthquakes can be. The 1999 generation of geologists had spent decades studying the Sunda subduction zone, but the events of December 2004 transformed public awareness forever. The giant Sumatra-Andaman earthquake demonstrated the power of a full-scale megathrust rupture. Yet while global attention focused on Sumatra, another section of the same tectonic system remained comparatively quiet: Java. Beneath the waters south of the island, the Indo-Australian Plate descends beneath Southeast Asia at approximately 50 to 70 millimeters per year, equivalent to about 2 to 3 inches or about 5 to 7.6 centimeters annually. The convergence rate is substantial. The trench is active. The geological ingredients for major earthquakes are present. So why has Java historically produced fewer giant events than Sumatra? That question continues driving research today. One possibility involves differences in sediment thickness along the trench. Another concerns variations in fault roughness. A third involves the distribution of fluids within the subduction interface. Whatever the cause, Java appears capable of producing a particularly dangerous phenomenon known as a tsunami earthquake. These earthquakes rupture unusually slowly. Because of that slow rupture velocity, they often generate weaker shaking than expected for their size. People may underestimate the threat. The ocean does not. Slow slip occurring very close to the seafloor can produce enormous vertical displacement. That displacement moves water, and moving water generates tsunamis. The 1994 and 2006 events demonstrated this danger vividly. Both generated destructive tsunami waves despite relatively modest earthquake magnitudes compared with classic megathrust giants. The key lesson is that earthquake magnitude alone does not determine tsunami hazard. Rupture depth, slip distribution, seafloor deformation. These factors can be equally important. Java remains under close scrutiny because geologists cannot rule out the possibility of a much larger rupture involving broader sections of the megathrust. If that happens, the consequences could extend far beyond Indonesia's shores. Number 7. The Guerrero Gap, Mexico. Few places illustrate the complexity of fault behavior better than the Guerrero Gap. Located along Mexico's Pacific coast, this segment of the Middle America Trench occupies a peculiar position in earthquake science. For more than a century, it has largely avoided the large earthquakes expected along a rapidly converging plate boundary. The Cocos Plate descends beneath North America at roughly 60 millimeters per year, equivalent to about 2.4 inches or about 6 centimeters annually. By conventional reasoning, a major rupture should have occurred long ago. Instead, scientists discovered something remarkable. The fault was moving, just not in earthquakes. Sensitive GPS networks revealed repeated episodes of slow slip. These events unfold over weeks or months rather than seconds. Entire sections of the plate boundary slide quietly. No violent shaking occurs. No buildings collapse. No tsunami warnings are issued. From a geological perspective, however, these events are fascinating. They demonstrate that faults possess more than two states. They are not simply locked or broken. They can also occupy intermediate conditions where friction weakens gradually. For years, researchers wondered whether the slow slip events were harmlessly releasing accumulated strain. The answer appears to be no. Detailed analyses indicate that the amount of stress relieved through slow slip is insufficient to balance the total plate convergence. The deficit continues growing, year after year, decade after decade. The result is a gradually increasing reservoir of stored elastic energy. That energy represents the potential for a future earthquake approaching magnitude 8 or greater. The Guerrero Gap therefore occupies a unique position on this countdown. It is not completely locked. It is not completely creeping. It exists in a hybrid state that remains one of the most important natural laboratories for understanding how megathrust earthquakes begin. The unsettling possibility is that slow slip behavior may not prevent a future rupture. Instead, it may simply delay it. And when enough strain accumulates, the transition from silent movement to catastrophic failure could occur with extraordinary speed. Number 6. Lesser Antilles Subduction Zone. The Caribbean is often imagined as a region of turquoise water, coral reefs, volcanic islands, and tropical coastlines. Yet beneath those tranquil waters lies a tectonic system that receives far less public attention than the Pacific's famous megathrusts. For geologists, however, the Lesser Antilles Subduction Zone has become increasingly difficult to ignore. Stretching in a broad arc from the Virgin Islands toward the coast of South America, this boundary marks the location where the North American plate descends beneath the Caribbean plate. The convergence rate is slower than many Pacific subduction zones, generally only a few tens of millimeters per year, roughly equivalent to 1 to 2 inches annually. At first glance, that slower rate might appear reassuring. It is not. Earthquake hazard depends on far more than convergent speed alone. The real concern is the relationship between convergence and release. If plates move toward one another but fail to release that motion through earthquakes, strain accumulates. It accumulates silently, invisibly, and relentlessly. Recent geodetic investigations have revealed exactly that possibility. Researchers comparing modern GPS measurements with historical earthquake records discovered something troubling. The amount of tectonic convergence occurring across portions of the Lesser Antilles exceeds the amount of slip released by known earthquakes. The difference is known as a moment deficit. Think of it as a geological debt. Every year the plates continue moving. Every year the fault fails to fully pay back that motion through rupture. The unpaid portion accumulates. Eventually the debt becomes enormous. Modeling studies suggest that portions of the Megathrust offshore Guadeloupe and neighboring islands may have accumulated enough stored energy to support an earthquake approaching magnitude 8 or greater. Such a rupture would not simply generate shaking. Its greatest threat would likely emerge from the ocean itself. Unlike continental earthquakes, shallow megathrust events directly deform the seafloor. Even a vertical displacement of only a few meters can move an astonishing volume of seawater. That displaced water becomes a tsunami. The geography of the Caribbean makes this especially concerning. Island chains sit close to the trench. Population centers line narrow coastal plains. Travel times for tsunami waves may be measured not in hours, but in minutes. There is another challenge. The historical record in the Lesser Antilles is relatively short compared with geological time. Many Caribbean settlements are only a few centuries old. Instrumental earthquake monitoring spans an even shorter period, but the rocks preserve a much longer memory. Ancient tsunami deposits discovered in coastal sediments hint that much larger events may have occurred before written records began. Layer after layer of marine sand buried within otherwise quiet coastal environments tells a story of sudden inundation. The ocean arrived, the ocean retreated, and then centuries passed. Those buried records serve as reminders that megathrust systems operate on timescales far longer than human memory. A fault can remain quiet for generations while steadily accumulating the ingredients necessary for catastrophe. That is why the Lesser Antilles earns its place on this list. Not because it is shaking constantly, but because it is not. Number 5. Hikurangi Subduction Zone, New Zealand. If earthquake science has taught us anything over the past 2 decades, it is that faults are far more complicated than researchers once believed. Few places demonstrate that lesson better than the Hikurangi Subduction Zone. Located off the eastern coast of New Zealand's North Island, Hikurangi is where the Pacific Plate dives beneath the Australian Plate at approximately 40 to 50 millimeters per year, around 1.5 to 2 inches annually. At first glance, the system appears almost contradictory. Some portions of the fault creep, other portions lock. Some sections produce slow slip events. Others appear capable of catastrophic rupture. All of these behaviors occur on the same plate boundary. For years, slow slip events fascinated researchers. During these episodes, sections of the megathrust gradually slide over periods lasting weeks or months. Movement that would normally occur during an earthquake instead unfolds in near silence. No destructive shaking accompanies the process. Sensitive GPS instruments are often required to detect it. Entire regions may move several centimeters without residents noticing anything unusual. Initially, some scientists wondered whether these events might reduce earthquake risk. Perhaps the fault was harmlessly releasing accumulated stress. The answer proved more complicated. Detailed observations revealed that the slow slip events occur primarily in specific regions of the plate interface, while neighboring sections remain strongly coupled. In other words, one part of the fault may be creeping, while another remains firmly locked. Imagine bending a thick wooden board. Some fibers begin stretching, Others remain rigid. Stress becomes concentrated in the strongest sections. Eventually, those sections fail. The same principle applies to megathrust systems. Along Hikurangi, geodetic data reveal major locked patches beneath portions of Hawke Bay and beneath regions extending toward Wellington. These areas continue accumulating strain despite the presence of nearby slow slip activity. That finding transformed scientific thinking. Slow slip was not necessarily relieving the hazard. In some cases, it might actually help identify where stress is concentrating. Then came the geological evidence. Marine sediment cores recovered from offshore basins preserved a remarkable history of ancient earthquakes. Layers of disturbed sediment, known as turbidites, indicated episodes of sudden seafloor shaking. Some deposits appeared consistent with earthquakes exceeding magnitude 8. The implication was unmistakable. Despite its reputation for slow slip behavior, Hikurangi has produced major megathrust ruptures in the past, and it remains capable of producing them again. Perhaps the most important lesson from Hikurangi is that quiet movement does not guarantee safety. A fault can creep today and rupture tomorrow. A segment slipping silently at depth may exist alongside another segment storing enormous amounts of energy. Nature rarely conforms to simple categories, and Hikurangi may be one of the most complex megathrust systems currently under investigation. Number 4. Puerto Rico Trench. Some megathrusts earn attention because of their frequent earthquakes. Others command respect because of what little we know about them. The Puerto Rico Trench belongs firmly in the second category. Stretching north of Puerto Rico and the Virgin Islands, this boundary marks one of the deepest trenches in the Atlantic Ocean. Here the North American plate moves beneath the Caribbean plate at approximately 19 millimeters per year, roughly 3/4 of an inch annually. Compared with Pacific megathrusts, the convergence rate seems modest, yet the geological evidence suggests that speed alone does not define danger. The challenge facing scientists is that this region occupies a tectonic gray zone. Part of the motion is accommodated through subduction. Part occurs along major strike-slip faults. The interaction between these mechanisms creates a complex network of deformation. For decades, researchers debated exactly how much earthquake potential the trench possessed. Then history began offering clues. The earthquake of 1787 caused widespread destruction across Puerto Rico and neighboring islands. Although precise measurements do not exist, modern reconstructions suggest a very large offshore event. Another warning arrived in 1918. A magnitude 7 class earthquake generated a destructive tsunami that struck Puerto Rico's western coast. The event demonstrated an uncomfortable truth. Even moderate megathrust earthquakes in this region can rapidly generate dangerous waves. The trench lies close to shore. Travel times are short. Communities may have little opportunity to react. More recently, geological investigations uncovered evidence for something even larger. Researchers studying coastal deposits identified tsunami sediments dating to a period between the late 15th and early 16th centuries. The scale of inundation suggested a much larger earthquake than anything documented in modern records. Some estimates indicate a rupture approaching magnitude 8.7. If correct, the finding dramatically expands the perceived hazard. Such an earthquake would involve enormous sections of the plate boundary and significant seafloor displacement. The tsunami potential would be severe. What makes the Puerto Rico Trench especially unsettling is the contrast between geological evidence and modern experience. Most residents have never witnessed a giant megathrust event. The region appears relatively calm, yet the sediment record tells a different story. The rocks remember earthquakes that people have forgotten, and those memories suggest the system remains capable of producing another great rupture. Number 3. Manila Trench, Philippines. Now we arrive at the first of the true giants. The Manila Trench occupies a unique position among Earth's subduction zones because it combines three ingredients that rarely occur together at such extreme levels: very rapid plate convergence, strong evidence of locking, and enormous human exposure. That combination is what elevates the Manila Megathrust into the upper tier of global concern. Off the western coast of Luzon, the oceanic crust of the South China Sea descends beneath the Philippine Mobile Belt and associated tectonic blocks at rates approaching 90 to 100 millimeters per year. That is approximately 3 to 4 inches annually. In geological terms, that speed is extraordinary. Every year, the plates attempt to move nearly the length of a human hand relative to one another. If that motion were released continuously, the fault would slide harmlessly. Instead, substantial sections appear locked. The plates are moving, the fault is resisting, the strain accumulates. This is where modern geodesy transformed scientific understanding. High-precision GPS networks, combined with marine geophysical surveys and numerical modeling, revealed that large portions of the megathrust are strongly coupled. Rather than slipping freely, the interface behaves like a giant welded surface. The implications become startling when projected across centuries. If convergence continues at roughly 100 millimeters per year, then a century produces approximately 10 meters, about 33 feet, of potential slip accumulation. 3 centuries produce roughly 30 meters, nearly 98 feet. That amount of stored displacement is sufficient to power one of the largest earthquakes on Earth. Indeed, several researchers have concluded that a magnitude 9 class rupture cannot be excluded. Some have argued that the accumulated slip deficit already approaches values consistent with such an event. The absence of recent giant earthquakes is not comforting. It is precisely why scientists are concerned. A fault releasing stress through repeated large earthquakes may avoid extreme accumulation. A fault remaining locked for centuries does not enjoy that luxury. The strain simply continues building. Then there is the geometry of the South China Sea itself. Unlike the vast Pacific Ocean, the South China Sea forms a comparatively enclosed basin. Tsunami waves generated by major seafloor displacement would interact with coastlines throughout the region. Energy would not need to cross an entire ocean basin before encountering populated shores. It would arrive quickly, and the populations involved are immense. Major urban centers, ports, industrial facilities, transportation hubs, and energy infrastructure line the surrounding coastlines. Millions upon millions of people occupy regions vulnerable to tsunami inundation. The geological mechanism is straightforward but terrifying. A locked megathrust accumulates centuries of strain. Friction eventually fails. The fault ruptures across hundreds of kilometers. The seafloor abruptly rises and falls. Water is displaced. Tsunami waves radiate outward. The entire sequence unfolds within minutes. For geologists, the Manila Trench represents one of the clearest examples of a rapidly moving, strongly locked, highly exposed subduction system. It is a place where the physics of plate tectonics and the realities of human geography intersect in the most uncomfortable way possible. And that is why it stands at number 3 on this countdown. Number 2. Nankai Trough, Japan. If there is one megathrust on Earth that has taught scientists the value of studying history, it is the Nankai Trough. Running along the southern coast of Japan, this subduction zone marks the place where the Philippine Sea Plate dives beneath southwestern Japan. The convergence rate varies along the margin, but generally falls between 40 and 60 millimeters per year, approximately 1.5 to 2.5 inches annually. On paper, those numbers are not extraordinary. Many other trenches move faster. Some accumulate strain more rapidly. Yet Nankai sits near the top of this countdown for a simple reason. Its behavior is frighteningly consistent. Unlike many megathrust systems that leave researchers guessing, Nankai has repeatedly demonstrated its ability to generate massive earthquakes throughout recorded history. For more than 1,000 years, Japanese chronicles, tsunami deposits, uplifted shorelines, and modern instrumentation have documented the same basic pattern. Stress accumulates. The fault remains locked. A major rupture occurs. Then, the cycle begins again. The remarkable aspect is how often this sequence has repeated. Historical records describe devastating events in the years 1096, 1361, 1499, 1605, 1707, 1854, and then again during the 20th century. Each rupture differs in detail, but the message remains the same. This megathrust does not sleep forever, it repeatedly returns. Scientists studying the trough have identified several major segments capable of rupturing individually or together. These sections are commonly referred to as the Tokai, Tonankai, and Nankai segments. Sometimes only part of the system breaks. Other times, multiple segments rupture in close succession. The earthquakes of 1944 and 1946 provide a classic example. The Tonankai section ruptured first. 2 years later, the Nankai segment followed. Together they demonstrated how strain can transfer between neighboring portions of a megathrust. When one section fails, stress patterns change across the entire fault system. The neighboring segment may suddenly find itself pushed closer to failure. This process is one reason why megathrust earthquakes can occur in clusters. The geological machinery behind Nankai is straightforward yet relentless. The Philippine sea plate continuously descends beneath Japan. Along much of the interface, friction prevents smooth movement. The plates lock together. The overriding crust deforms. Land slowly bends and warps. Global navigation satellite system stations across Japan reveal these motions in extraordinary detail. Measurements collected over decades show that the very regions which ruptured during previous earthquakes remain strongly coupled today. In other words, the fault has largely reset itself. The spring is being compressed once again. Perhaps the most dangerous aspect of Nankai involves the shallow portion of the megathrust near the trench. When rupture propagates into these shallow regions, the seafloor can experience significant vertical displacement. That displacement transfers directly into the ocean above. The result is tsunami generation. Japan's historical records contain repeated descriptions of this phenomenon. Entire coastal communities were devastated not only by shaking, but also by walls of water arriving minutes later. In some cases, the tsunami caused more destruction than the earthquake itself. Researchers have also identified evidence for what are known as tsunami earthquakes along portions of the Nankai margin. These events rupture more slowly than typical earthquakes and can generate unexpectedly large tsunamis relative to the shaking people experience on land. Such behavior complicates hazard assessment because human perception of shaking may underestimate the severity of the unfolding event. Today, Nankai remains one of the most intensively monitored faults on Earth. Dense global navigation satellite system networks track crustal deformation. Ocean bottom sensors measure pressure changes. Seismometers watch for unusual activity. Scientists continuously update models of coupling, stress accumulation, and rupture potential. Yet despite all this monitoring, one fundamental reality remains unchanged. The fault is still loading. The plates are still converging, and history suggests that the cycle is not over. That combination of strong locking, repeated historical ruptures, enormous population exposure, and well-documented tsunami potential places Nankai near the very top of the global hazard list. But there is one megathrust that edges even higher. One fault whose silence may be more alarming than any historical pattern. One boundary where centuries have passed without a major rupture, even as evidence of accumulating strain continues to mount. Number 1. Cascadia Subduction Zone. The most dangerous megathrust on this list is not the fastest, it is not the longest, it is not even the most seismically active. Its danger comes from something far more unsettling. Silence. Stretching nearly 1,000 kilometers, approximately 621 miles, from Northern California through Oregon and Washington to Vancouver Island, the Cascadia Subduction Zone marks the place where the Juan de Fuca Plate descends beneath North America. The convergence rate averages roughly 40 millimeters per year, about 1.5 inches annually, or about 1.6 centimeters annually. That rate is modest compared with the Manila Trench. It is slower than Chile. It is slower than parts of Alaska. Yet Cascadia occupies the #1 position because of the extraordinary mismatch between tectonic activity and earthquake activity. The plates continue moving. The fault continues locking. But large earthquakes have been absent for more than 3 centuries. To understand why this matters, we must look beyond human history. For generations, settlers along the Pacific Northwest believed the region was relatively safe from giant earthquakes. No one had witnessed a magnitude 9 event. No written record described one. The fault seemed dormant. Then geologists began examining the landscape. What they discovered transformed earthquake science. Along estuaries and coastal marshes, researchers found ghost forests. These were stands of trees that had suddenly died centuries ago after their roots were submerged beneath seawater. The trees had not died gradually.
They had died abruptly. Something had caused the land to drop. Elsewhere, scientists discovered sand sheets buried within coastal sediments. These layers extended across enormous distances and could only be explained by tsunami inundation. Offshore, marine cores revealed repeated sequences of turbidites, underwater landslide deposits triggered by intense shaking. Piece by piece, the evidence accumulated. A pattern emerged. Cascadia had produced not one giant earthquake, but many. At least 19 major ruptures occurred during the past 10,000 years. The fault was not dormant. It was operating on a timescale longer than human memory. The final breakthrough came from across the Pacific Ocean. Japanese historical records described an unusual tsunami arriving on January 26 of the year 1700. No local earthquake had been felt in Japan. The source remained a mystery for centuries. Eventually, researchers connected the dots. The tsunami had crossed the Pacific from Cascadia. The date matched tree ring evidence from drowned forests in North America. For the first time, scientists could identify the precise date of Cascadia's last great earthquake. January 26, 1700. The rupture likely exceeded magnitude 8.7 and may have approached magnitude 9.2. More than 300 years have passed since then. During those centuries, plate convergence never stopped. The Juan de Fuca plate continued descending. North America continued resisting, and the fault continued storing strain. Modern global navigation satellite system observations reveal this process in remarkable detail. Large portions of the Megathrust remain strongly locked. The coastal region is slowly deforming as stress accumulates. Some areas are rising by millimeters each year, equivalent to tiny fractions of an inch. Others are gradually tilting. These subtle motions represent stored elastic energy. The crust is being bent like an enormous spring. One day, that spring will release. The mechanics of a future Cascadia rupture are sobering. A fault extending hundreds of kilometers could break in a matter of minutes. Several meters of slip could occur along the plate interface. The seafloor would rise and fall. A major tsunami would be generated. Shaking could persist for several minutes across large portions of the Pacific Northwest. Unlike regions accustomed to frequent large earthquakes, Cascadia's long, quiet interval creates additional vulnerability. Much of the modern infrastructure has never experienced a megathrust event. Millions of residents live in communities that did not exist during the last great rupture. Ports, bridges, highways, power systems, and communication networks have developed during an unusually calm period. Geologically speaking, that calm period is an illusion. The fault has not been inactive, it has been loading. This is why Cascadia consistently ranks among the highest priority earthquake hazards in North America. Not because scientists know when it will rupture, they do not. Not because it is overdue. Earthquakes do not obey schedules, but because every major line of evidence points in the same direction. The fault is locked, the strain is accumulating, and the geological record proves that giant earthquakes are part of its natural behavior. As our countdown comes to an end, a deeper lesson emerges. The world's most dangerous megathrusts rarely advertise their intentions. They do not necessarily produce swarms of earthquakes. They do not always generate dramatic warning signs. Many of them spend centuries doing almost nothing visible at all. Yet beneath the surface, the physics never stop. Tectonic plates continue converging. Friction continues resisting. Stress continues accumulating. The Earth operates according to mechanical laws that care nothing about human timelines. From Alaska's reloading rupture zones to Chile's shifting locked patches, from Java's deceptive tsunami earthquakes to Mexico's slow slip mysteries, from the hidden strain of the Caribbean to New Zealand's complex creeping fault, from Puerto Rico's prehistoric tsunami evidence to the rapidly converging Manila Trench, every location on this countdown tells the same story. Silence is not safety. In fact, silence can be one of the most important warning signs of all. The greatest earthquakes on Earth are born not from chaos, but from patience. They emerge after decades, centuries, or even millennia of accumulation. A few centimeters each year, a few inches each decade, a few feet each century, tiny motions building toward immense consequences. Somewhere beneath the oceans tonight, the process continues. The Pacific Plate is still descending beneath Alaska. The Nazca Plate is still driving beneath Chile. The Indo-Australian Plate is still pushing against Java. The Cocos Plate is still pressing beneath Mexico. The North American Plate is still converging with the Caribbean. The Pacific Plate is still diving beneath New Zealand. The Manila Trench is still accumulating strain. The Nankai Trough is still loading, and Cascadia is still waiting. No one knows which of these giants will move next. But geology leaves little doubt about one thing. The forces are already in motion, and they never stopped.